Hello, 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 hello. Pardon the 10-minute wait time, but we had some technical difficulties and had to get a little creative. We're here. We're doing it. How's everybody doing tonight? All right. Did anybody get blown away by the wind yesterday? That was not great. It felt like a racket. Hold on. Find it. Okay, we're good. All right. Hello, everybody. My name is Aaron. This is Michael.
Hi.
That's Sam. Got Adam and Brian running the show. We got Thomas. He is I was gonna say he's online. We're not live streaming right now. That's why you had to get creative. So he's watching in spirit. How many first timers out here tonight? Anybody? Great. Cool. Glad to have you. And then everybody else, been here, done that, a couple of times, been around the block? Within five? No, like first five. Oh, yeah. Well, yeah, within five. If after five, you're a veteran. Also, I didn't say everybody. Also, we got Erica running the show. We got Jasmine running the show. Caleb is en route, I guess, actually. We don't know if he's going to be here. Okay. We got Jasmine. We got to add Jasmine for Astronomy News. So for the first timers, probably wondering what is Astronomy on Tap. You might be a little familiar. It's pretty boilerplate. But Michael, what is Astronomy on Tap?
Well, Astronomy on Tap is a worldwide phenomenon, as I like to say. And we can see here on our updated map for our regulars, you notice that the pinpoints are different. Why? Because we've updated it. This is very fresh, hot off the plate locations.
Mostly where they drink beer, I think.
Yeah. The yellow one is us, of course, over here. Plenty in the United States, but plenty in Europe, South America, and Asia. So we're spread around. It's a lot of fun. But what makes ours so special? Well, we are fun. Not to toot our own horn, but I feel like everybody here will enjoy tonight. As you see there, that's a good slide for that one because, we do have our drinking words during our talks, so everybody drink responsibly, but have fun. Very interesting. Both speakers tonight are talking about very relevant fields right now in planetary science. One of them will be about Uranus, which is the next flagship target of NASA, and planetary defense, which is, of course, very important so that those asteroids don't get too close to us. We are interactive. You all will have a chance to ask questions with our phone line here. And a chance to win at the end of every AOT. We do prizes and trivia. And I'm happy to announce that Robert Reeves, who has been donating our Lunar Orbiter prints, the last time we told you that was coming to an end, I have an amendment to that statement. It is not coming to an end. He's been given more. It's fake scarcity. He's driving up the... No, but if people seem to enjoy having that as a prize, so we will continue having that as a prize for people moving forward, and we'll make sure that it goes to new people too, because some of y'all have too many of those. All right, tonight's program.
All right, today we have an excellent lineup of speakers. Our first presentation will be Dr. Maryame Moutamid on why we should explore the planet Uranus. Then we'll have Astronomy in the News, a classic. And then our first and last line of planetary defense by Aaron Deleon. Interestingly, when we made the official link that combined the two titles, and I thought if you combine the two titles, it's pretty funny, why we should explore the planet Uranus, our first and last line of planetary defense. So it's got some big shoes to fill. All right. Tracy, could you please come up here? I'm stalling. I'm just kidding. I could talk all day. Take your time.
Okay, so I have the great pleasure of introducing our first speaker. Maryame Moutamid is a colleague and friend. Born and raised in Morocco, she completed her undergraduate studies in Paris, France, and later earned her PhD at the Paris Observatory and Paris Science et Lettres University. I'll go with that. I don't speak French. Afterwards, she moved to the United States for a postdoctoral research position at Cornell University, where she later became a senior research associate at the Center for Astrophysics and Planetary Sciences at Cornell. In March 2024, she joined the best institute in the world, Southwest Research Institute, but in our Boulder office, so, minus 1 point deduction. As a lead scientist, her expertise lies in orbital dynamics, celestial mechanics, and spacecraft data analysis. Currently, her research focuses on planetary ring dynamics, satellite orbital dynamics, and their connections to the interior structures of giant planets. So please give a big welcome to Dr. Moutamid. And drinking word? Huh? The drinking word is?
Uranus.
Uranus. A quick reminder that we are not responsible for you driving home, so please play safely.
Okay. That's too early. Thank you, Tracy. Thank you, everybody, for having me today. So I'm very happy to share some work and talk about the planet Uranus. So Uranus is a unique planet. It is a unique planet, first of all, because of its color. It has this beautiful cyan color. And it also has an interesting name. There is actually Greek gods. All the planets in the solar system has a Roman god except this planet. It's also embarrassing to pronounce this name, but I was born and raised in Morocco, so we have a different pronunciation, so I don't really mind. That's your problem, not mine. So I figured that later on in life, that it is really embarrassing. Anyway, so the diameter of this planet, it's more than 60 times the diameter of Earth, so it's considered a giant planet, but not as big as Jupiter or Uranus, for instance. It's called ice planet, ice giant or gas giant, but actually ice, it's a wrong name, and also giant gas planet, it's also a wrong name. I will tell you later on why, but we are really lacking of a classification of the planet. So if you have a clever way to classify this planet, I would like to take suggestions. So this planet was discovered by this handsome man. His name is William Herschel. It was about in the 18th century. And he was in his yard, in home, and he has a reflective telescope, and he followed the orbits of Uranus. So he actually found out that the orbit of this planet is very slow, it's very strange. It does not look like an orbit of a planet. But just to be fair, before him, a lot of people look at this planet and they thought it was a star or something different, except that he figured out that it is a planet. We should accept that it is a planet. It just had a strange orbit. We will deal with that later. And later means that Leverrier later on find out another planet called Neptune in our solar system, that it is responsible of slowing the orbits of Uranus. All right, another particularity about this planet is that all the other planets, for instance, Saturn, Jupiter, Earth, all the other planets in solar system are spinning like a ball on a plane. So it means that the pole is actually perpendicular to the equator of the solar system, except that Uranus is not really orbiting in a perpendicular, almost perpendicular to the equator. Uranus actually is rolling on its, Uranus is rolling, meaning that the pole, okay, the planet, the blue planets, depending if the North Pole is here or there, the pole, one of the pole is actually facing the sun for about half of the orbit. That is very particular in the solar system. So the rotation of the planets around itself, it's only 17 hours. However, the revolution around the sun is about 84 years. So if someone here is 84 years old, they can say that I am 1 year old in the Uranian system. I am about 5 months old. So during the solstice here, this planet shows actually the same pole, say this is the North Pole, for about 42 years. And then here we have the equinox, where the equator is facing the sun, and then for the next other 42 years, the South Pole is facing the sun, meaning that one pole is facing the same star, our sun, for about 42 years. So it's getting really hot for 42 years. The other pole is dark for 40 other 2 years. This is very particular, and we think that this is due to some other dynamical phenomena that happened in the past that I can talk about it later. So this is unique for this blue planet. I'd like you to drive safely, so. So another strange thing about this planet is that even if it's rolling on its orbit around the sun, meaning that the pole is showing the same side to the sun, actually the energy at its pole is going to be much higher at the pole than at the equator, because the sun is facing this point instead of here. That makes sense. But when people measure the temperature at the pole than in the equator, it seems like the equator is much hotter than the pole. We don't know why. The title of this talk is Why We Should Explore the Planet, so I will provide more question than answer. We have a lot of questions about this planet that we need a spacecraft around it as soon as possible. All right, so theory speculate that at the beginning of the formation of the solar system, Uranus was formed like all the other planets, and then around Uranus, around this planet, there were a lot of bodies at the beginning of the solar system, and somebody about the size of the planet Earth get closer to the planet and hit the planet. There were a big collision here, and after the collision, the spin of the planet rotates about 90 degrees. And since then, Uranus never recovered from this tilt. So we stay in this configuration for a long time, as of now. So this is theory, but it is the most solid theory that we have about the spin of the blue planet. So how big is Uranus? Yeah. It is about 5, can you change the word? It is about 14 times the mass of Earth, and it is about 60 times the diameter of Earth. However, Neptune is more massive. It's about 17 times the mass of Earth, but it's only smaller than Uranus. It's only about, okay, it's much smaller, meaning that the density of Uranus is less than Neptune. Okay, what it is made of? We think that the blue planet is made of 3 main layers, or actually 4 of them. The first one is a core, a solid core at the center, made of silicate and rock. The size of this core is only half of the mass of Earth, and its diameter is about 1/5 the size of the planet. After that, we have what we think a mantle surrounding the core. The mantle mass is about 13 times the mass of Earth, and it's about 60% the size of the blue planet. It is the mantle here, this one, is mainly made of water, ammonia, and methane. It is extremely hot. It's about 5,000 degrees Celsius, which is 9,000 degrees Fahrenheit, because we are in the United States. Sorry, this is the right value, 9,000 degrees Fahrenheit. So even we say it's an icy giant, it's not really fair to say so because the temperature here is so high and the pressure here is so high that we think that this mantle is mainly liquid ocean surrounding the core. Not all water, but mainly ammonia and methane and water. So around this mantle, we have an atmosphere, a thick atmosphere. The size of this atmosphere in terms of mass is about half the size of Earth, and it's also 1/5 of the size of the blue planets. It is mainly made of hydrogen, helium, and a tiny amount of methane. Then around this atmosphere, we have a tiny layer on the top. Because of this small amount of methane, it's only about few percent that we have the cyan color. It's the methane that is responsible of this beautiful color. Okay, so I said something about the mantle. It is made of water, that's H2O, ammonia, and methane. Methane is CH4. It's carbon and 4 atoms of hydrogen. Then we have a lot of high temperature, as I said, 9,000 degrees Fahrenheit, and high pressure. So what that mean? It means that the methane that it is, for instance, made of carbon and hydrogen, mainly. For carbon, we break the methane molecule, and then we compress all the carbon atom. What happened to the carbon with a high temperature and high pressure? Sorry. It's brand new, so that's why. Thank you. Thank you very much. Okay, I shouldn't have a drink. So this is an interesting theory, but it is not that crazy. So what people think is that around the mantle, since we have compressed atom of carbon, under temperature and pressure, we have a ring of diamonds that are precipitating around the core, and we think that the core surface is actually full of diamonds. So if you want to get rich, we should go to Uranus instead of Mars. Instead of Mars. No comments. No. Anyway, so, but no, this is just a joke about, we cannot really go in the interior, of course. If I go there, it's not worth it. I am also made of carbon, so if I go there, I will be diamonds. It's not really worth it. I'd rather live than be something crazy like this. Anyway, so it is really worth understanding this interior because we know also that the magnetic field of Uranus is not really acting as it should be. It is shifted from the center. It's not even at the center. We don't even think that the source of the magnetic field is the core. It can be probably the mantle or something else, or all these diamonds that are making the magnetic field shifted by a lot. Okay, so let's fly a little bit far away from the planet, the blue planet or the cyan planet. So we have here a sketch. Here we have Uranus. Here we have the dense, compact ring system around it. And here we have the inner moons. We have about 13 inner moons, and here we have 5 major moons, and outside the 5 major moons, we have another irregular satellites. So let's talk about the rings. So here it's a zoom of the rings. We have what we call the zeta ring, sorry. Changing this to PDF make this a little bit funny, but it's called the zeta ring. It's dense. Actually, it's not dense. It's very diffuse. It's made of particles, mainly ice and silicates and other components that are very tiny. It's only micrometer in size. Then we have 6, 5, 4, alpha, beta, etc., until epsilon, which are 9 moons, 9 rings that are very thick. It means that there is a lot of material within a small amount of space. They are narrow, as you can see. The edges are very sharp. And the width of these rings is only a few kilometers. This is the epsilon ring, which is the most visible ring of the blue planet. Then we have the inner satellites. We have about 13 of them in here. Then we have the new ring, which we think is associated with the moon that it is feeding this ring. The new ring is just like the zeta ring. It is made of micrometer size particles. However, the other rings here, the sharp one, are made of centimeter to meter size particles. Then we have other moons here. This is the biggest inner moon. Then we have the mu ring that we think it's fed by this moon called Mab. So Mab is very tiny, it's 10 kilometers in size, meaning that the gravity at the surface is very small, meaning all the particles that we are around here are actually leaving the surface of Mab, feeding the mu ring. We think the same thing happening here and here, except that we don't have moons yet detected. All right, this is a Voyager image. Voyager visited the blue planet in 1986, almost 40 years ago. So it's about time to go back. So this is a nice Voyager image where we have these rings that you see. They are very sharp. They are easily detected. Their width is only about a few kilometers. And this is the Epsilon ring, which is the brightest one. So theory predicts that ring, as you know, it's dust, it's ice, silicate. When you leave particles like this in the space, they will just spread out. They will not stay at the same position. However, we are observing them, and we are observing them for a while, meaning that there is a mechanism that it is confining them and stopping them from spreading in space. For the Epsilon ring here, which is this one, we have two moons called Ophelia and Cordelia. Both of them, actually, Cordelia is here and Ophelia is here. This moon is applying a torque, a gravitational torque, to stop this edge from spreading in this direction. And this one is applying a gravitational torque to stop this edge, the outer one, from spreading in this direction. So the ring is trapped between two moons. We call them the shepherding moons. That's just like we shepherd animals. This name, this mechanism is true for the Epsilon ring, for another ring in the solar system called the F ring, around Uranus, and for around Saturn, actually, sorry. And we think that for these sharp edges here, we should have a lot of moon for each side of each ring that are playing the same mechanism as Ophelia and Cordelia, except that we don't see anything yet. So again, we need to go there to detect new moon. If you want to discover new moon, you should vote for getting the Uranus orbital and probe. All right. So other colleagues think that if we don't find any moon, maybe there is another mechanism related to the interior of the planet that it is confining the ring. But I'm not going to go there because it's a little bit more complicated, but it's the same idea. So let's talk briefly about the moons. So we have three categories of moon. We have the inner one. See the size of the planet here, getting smaller and smaller. The inner moons here, we have 13 of them. We have 5 major moons. They are much bigger. Those are the orbits. For instance, the outmost one is Oberon. And then here we have the irregular moon that are very far away from the planet. So the irregular one, we think that they are trapped objects from other systems in the beginning of the formation of the solar system. Here we have the major moon, the 5 major moon. Miranda, Ariel, Umbriel, Titania, and Oberon. These two have about the same size. These two have about the same size, and this one is the tiniest one. For these 4 moons, we think that they are made mainly of 50% rock and 50% ice. Miranda is made mainly of ice. And we also think that they are differentiated, meaning that there is a core, a mantle, very likely an ocean, a liquid ocean, and a thick ice shell. So to understand and to verify this assumption, we need to go there using the Uranus orbiter and probe. All right, this is my last slide. Those are the inner moon. It is really interesting to understand the relationship between the inner moon and the rings. So previous studies showed that around Uranus, the ring here are very dark. You cannot see the contrast in color, but these rings are darker than the inner moon, and the inner moon are darker than the major moon. So there is a trend. The closer you get to the planet, the darkest the object became. This is very interesting. And it is exactly the opposite of what we are seeing in the system of Saturn. The closer you get to the planets, the brightest the particles became. Here we have mainly water ice, and here we have water ice and some silicates, and here we have mainly silicates, a big amount of silicates and rock. So the reason why we think this is happening, this is just observation. Now we have to explain it, how we are going to explain it. So we have what we call here the synchronous orbits. This is the only mathematical things I'm going to talk about in this talk. It's, imagine you have the rotation of Saturn, of Uranus is about 17 hours. This one need less time to make a total revolution about the planets. If you put a moon here at the synchronous orbits of the planets, we need 17 hours, which is equal to the rotation of the planet. We call this the synchronous orbit. It's synchronous because the revolution period is equal to the rotation period. So believe me if I say all the bodies that are inside the synchronous orbits will migrate inward, and all the bodies that are outside the synchronous orbits will migrate outward. The synchronous orbit of Saturn is much closer because it's only 10 hours. So everybody is migrating outward. So we think that something hit the planet, form a lot of material around here, rocky and silicates and not really clean, not a lot of ice. Everything shifted because of 90 degrees. And then these moons start to migrate inward and form rings, which is exactly the opposite of what we are seeing on Saturn. Since the synchronous orbit is here, the rings are spreading in the radial direction and then forming moons. That's why we think that the ring of Saturn are about 1 billion years, while the ring of Uranus are about only 600 million years. So the future is the Uranus orbital and probe. There are a lot of young people here. This is really the future. Uranus orbital and probe is, this flagship is gonna be the next priority. It is the next priority of the Decade Survey. The Decade Survey is just a group of people who are very smart and very important. They meet every 10 years, and they decide what is the next flagship. So they decided that this blue planet is the next priority, and we think that we can prepare a nice mission in next 10 years. And then to get there, we need 10 more years. So in 20 years, we will have the first data of this blue planet using this flagship. So 20 years is scary. We will be, some of us will be very old or not around, but the hope in the young generation is to study mathematics, physics, astronomy, and science in general, because this is your mission. Thank you.
All right, thank you so much for that amazing talk. Reminder to please text your questions into the phone number on the TV screen. So our first question is has Uranus's sun-facing side changed enough since the Voyager mission for relevant, or Voyager 2 I should say, for relevant science studies, like studying hemispherical changes or a different side of the planet?
So I believe that the last equinox happened in 2007, when the equator was facing the sun instead of the pole facing the sun. So meaning that the next equinox will happen in 42 years, from 2007, right? Yes. So to study what? What parts of the?
To study hemispherical changes, or just looking at a different thing than Voyager 2 did?
Yes, so Voyager visited Uranus in 1986. That was 39 years ago. So I have to do the math. 39 years ago. The equinox happened in 2007, which is how long? Which is 18 years ago. So maybe in 42 minus 18. I had 42 minus 18, it's 24, right? So in 24 years, we will have the next equinox, and then we can study again the planet and the equator of the planet.
All right. The next question is about the rings. Why are they separated the way that they are? Is it more than just the moons, like, or just what exactly you were talking about?
That's a great question. It's really, we don't know exactly why. It's a very strange system of ring. They are compact, they are very close to each other. They are narrow for most of them. So maybe there are moons there that we did not detect yet. They are very dark, unlike the other ring in the solar system. There are speculation about the formation of the rings from the moon after the impact with a big object a while ago, but we don't know what is the time scale of that and when it exactly happens. So we need an orbiter and probe to answer these questions.
Right. Yeah. And then, so for the equator, the phenomenon where it's hotter than the poles, is there a current leading theory based on what we've seen already, or?
For the equator?
Yes, the reason that it is hotter than the poles. Is there like a theory? Or
I don't think we know very well. It should not be hotter. It should be cooler because we are facing the pole most of the time, about 42 years. So, and the equator is seeing the sun only at the time of the equinox. So I don't think we know a great theory about that. Yeah. So it's more question than answers for the planets.
Do the moons of Uranus orbit its equatorial plane or the ecliptic plane?
Say again?
The moons of Uranus, do they orbit?
Yes, they are actually, all of the system is tilted by about 97 degrees. So if you observe Uranus now, at this time of its year, it should be facing on. Like we can see the planets and the rings around them as well as the moons. So everything is facing on, yeah.
What kind of ices would the major moons of Uranus likely be made of?
We think it's mainly rock and silicates. What kind of ices?
Like water ice
Yeah,
or
water
ammonia
ice.
or
The moons, except for Miranda, the other major moons are made 50% of rock and 50% of ice. For Miranda, it's mainly ice. Yeah, water ice.
Is Uranus observable with Earth-based telescopes such as Hubble or Webb?
Yes, Uranus was observed by the HST, the Hubble Space Telescope, by the Keck telescope. The only flyby that we had is Voyager, 39 years ago. And actually, the Zeta ring that I showed earlier was discovered by the Keck telescope. Yeah, and we are observing it now with the GWST, which is the James Webb Space Telescope.
Cool.
It's not Earth-based, but it is close to Earth than Uranus.
What dictates the naming convention for the rings? Why are there some that are Greek letters and some that are numbers?
I wish I knew. I know for like letters, like numbers actually, like 6, 5, 4. I don't know. I know for the moon it's Shakespearean characters, right, and Alexander Pope. For the rings, I'm not really sure. Sorry.
Let me see, there was one more. Given how given how far Uranus is from the sun, why is it in general so hot? Is it just all pressure?
Yeah, it's usually when a body is big enough, it has its internal heating that it creates enough heat to melt the layers around the core. And if Uranus was so tiny, you wouldn't have any internal heating.
What we know about its magnetic field is from that one Voyager flyby. Is there room for error within that one measurement, or are they pretty sure? Yeah.
Yes, there are always room for error. We are sure that the magnetic field is asymmetric. Right. We can measure that. It's not symmetric. as it should be. So theories are left to say that this magnetic field is not necessarily generated by the core. It is probably generated by something else, something in the mantle. But this is very speculative as of now. The more data we get, the more science we can get and more answer we can get.
All right, and then the last question is looking to the future. When is the best time to launch the mission so that it gets the best science?
Okay, let me think. I think that the goal is to send the mission in less than 10 years from now. If we want to get there about 20 years, that will be the equinox time. That will be the best time, and also to have Jupiter assistant gravity to for less cost and more time, to save time in getting there. If we miss that, it will be very difficult. Yeah. But again, I'm not really into space exploration, but I think if I believe the engineers, we should we should get there in 20 years from now. Yeah.
Sounds good. All right. Well, then let's hope we do get there, and let's thank our speaker once again. Thank you so much. All right, we are going to take our 10-minute break. We'll reconvene with Astronomy in the News at 7:55. Please make sure that you don't crowd the bar. If you're going to order from your wait staff. Check out our swag table, as I'll call it. We don't really have merch yet, but we got swag. And stick around. Oh, and sign up for our email list if you haven't already. I don't know where did we lose the QR? Yeah, but I don't see the QR slide. No, I know, but I. The QR code's not available today. Neither is our fun trivia or the Did You Know? Maybe Sam remembers it by heart.
I'm sorry, Sam. I deleted it on accident.
News, it's my turn now.
All right, hello everyone. Welcome to Astronomy News. I'm Caleb Guimar,
I'm Jasmine Singh.
and we'll go ahead and do the Astronomy News rundown for tonight. So, a number of rather interesting things going on. First and foremost, I will begin with what is in the skies this evening, and of course for much of the rest of the month. So, if you look up at the skies mid-month, about 9:30 p.m., by the way, daylight savings time starts this weekend. Remember that, Sunday morning, the clocks spring forward. So you do have to go out a little later in order to have a dark sky. But nonetheless, though, if you go out at that 9:30 p.m. time, you will have all of the wintertime stuff, mainly the constellation of Orion the Hunter, setting over there toward the west, and the springtime stuff, mainly the constellation of Leo the Lion, best marked by that backwards question mark shape with the bright star Regulus and this little triangle shape back end here. It will be rising over in the east, as well as the very familiar pattern of stars that we call the Big Dipper, more officially known by its actual constellation, Ursa Major, the Great Bear. So, straight overhead, much of the month, you will have Jupiter and Mars, but if you look over toward the horizon at sunset on the 13th, you'll be in for a nice treat. You will see the planets Venus and Mercury right next to each other in the sky. Mercury will be a little on the dim side. However, Venus, I don't think that helped much. Venus will be a little will be very, very bright, very apparent. So if you can find Venus, you can probably just look a little over and find Mercury. And then make sure if you're under a very dark sky, scan along that Milky Way for all these nice star clusters and star-forming nebulae, particularly right now, the Beehive cluster, which is right there at the crux of that upside-down Y shape of Cancer, which if you follow the belt of Orion down toward the left, it leads to the extremely bright star Sirius. You cannot miss it. Right beneath Sirius, if you look with a pair of binoculars, this is star cluster M41. It'll just be a kind of peppering of stars. They're both very young, very recently formed group of stars. Now, if you are a very ambitious sky watcher, toward the end of the month, find a dark site to go to near the time of new moon, and look for all 110 of the Messier deep sky objects from sunset to sunrise. I have done it before. I have scored 108 out of 110 of the objects myself. All right, thanks. I only missed the first one to set and the last one to rise. So it can be done. But again, for those of you that are very ambitious sky watchers, do so. And then, of course, we have a total lunar eclipse next week. Yes, it will be very late Thursday night, basically Friday morning that week. If you go out at about 2 o'clock in the morning, you will find that nice blood red moon in the sky. That's a simulation of what it will look like. Look over to the south, and you'll find that big, bright full moon there in the sky between Leo and Virgo. And again, at 1:59 a.m. is when peak eclipse will be. And if you watch in a couple hours leading up, you'll find it getting increasingly more blocked out in the sky, and then of course redder as the night goes on. And with that, I will go ahead to the news stories and let Jasmine take over from there.
Thank you. All right. So, of course, I have to start with Europa Clipper because I'm a little biased, you know. But Europa Clipper recently flew by Mars on the 1st. If you actually went on the Eyes of the Solar System website, like me and Michael did, you could actually see it go by in real time. It was really fun to watch. But basically, yeah. So it's flown by Mars, and it's used the gravity assist. And so its next big milestone will be the Earth gravity assist, which will not be until the end of next year. So we'll use that gravity assist, and then that'll help us eventually get to Jupiter. So really exciting stuff with Clipper. I think we'll get some stuff from the Mars flyby, but that won't be for a few months. So be on the lookout for that. Oh, wrong way. All right. And in the more commercial sector, Firefly, the private aerospace company. Their Blue Ghost lander just landed on the moon. I have some friends that work for them, so that's really exciting. They're based in Austin, so just down the road from us. It is the second private spacecraft ever to soft land on the moon. The first one was Intuitive Machines last year, and coincidentally enough, Intuitive Machines is going to try again tomorrow, I think, right? Tomorrow? Yeah, tomorrow to do it again. So that's really exciting. Be on the lookout for that. This spacecraft has this lander has 10 NASA instruments aboard, and they're going to be operating for 1 lunar day, which is approximately 2 weeks on Earth. And this is part of the CLPS program, which sends NASA science instruments on private spacecraft, and it kind of saves money, and they're doing this to collect data for future Artemis missions. So this is a really cool image, actually. It was part of a video. I didn't know if the video was going to work, so I just put the image of the shadow of Blue Ghost on the moon, and right there, that's us. That's Earth. And then this one is a lunar sunrise, which was captured by Blue Ghost, which I thought was really, really cool, so I put that on there. So, yeah, Blue Ghost on the moon. Not a hard landing. All right. You see, it was on the moon very softly. It didn't, crash on the moon. I don't know. I'm just making it up. But I'm going to guess it has to do something like that. Close enough. Now for James Webb News, we have found a complex atmosphere. Excuse me, Michael. Okay. We have found a complex atmosphere of a starless super Jupiter. What does that even mean? So, this planet, I was laughing at the name. If you know, you know. Yeah. All right, so it's a rapidly rotating, free-floating object, about 13 Jupiter masses. So it doesn't orbit a star or anything. It's just kind of hanging out. It's only about 20 light years away in the Milky Way, so not too far from us in the grand scheme of the universe. And it might be a brown dwarf. It's not quite an exoplanet or anything, so it's kind of a weird classification. So we had previously observed this planet object, but Webb had revealed a more complicated atmosphere than we previously thought. We had variations in cloud layers, temperature fluctuations, and different carbon chemistry. So you can see here the complicated plot. It's really not that. It's we have some few waves showing different near IR wavelengths coming from this object as it rotated, and it's thought to be from different atmospheric features, so different clouds, and then high altitude, hot and cold spots. And then on the right, we have the predicted structure of its atmosphere, which these arrows correspond to these different wavelengths. So this is a really interesting object, and I'm very glad that with James Webb, we've been able to find more stuff than before. James Webb's kind of, expanding what we've known before. So there we go. Thank you.
All right, so now we'll go ahead and give you some information about some upcoming events that you will want to be watching. I mentioned last month that by now SphereX and Punch would be launched. They have not launched quite yet. Several delays. So toward the end of this week, actually March 7th, this Friday, SphereX and Punch missions will be launching. Punch is a Swery-led mission, actually. Yeah, all right. So do we have any Punch folks in here this evening? Anyone? Oh, okay, all right. Yep, so there's, so anyway, a really great mission concept to be able to observe the sun's near environment, basically the corona, and its interface with the interplanetary medium. So again, very, very interesting mission. And in SphereX is a near IR optical sky survey telescope, basically meant to do this large survey mapping of the distribution of material between the galaxies and of course within our own galaxy. So very interesting stuff. Again, launch plan for this Friday, don't miss it. Intuitive Machines, that is actually a photograph from the Intuitive Machines IM-2 lander around the moon right now. They will be landing on the moon on March 6th. That is tomorrow, yes. That is roughly noontime, almost 11:32, so don't miss that. That will be something really fascinating to watch. Another Texas company based over in Houston, so best of luck to them as well. And then SpaceX Crew 10, NASA SpaceX Crew 10, they will be launching to the International Space Station on the 12th so far. So they will go up, and then after they go up, there will be a little bit of a changeover in Crew 9, which has Butch Wilmore and Suni Williams on board, who may or may not be stranded there. Anyway, they'll be returning on Crew 9 after that point. So a lot of stuff to look forward to. Astronomy events coming up. Don't miss UTSA Observatory / San Antonio League of Sidewalk Astronomers observing this Friday, March 7th. We will be observing at the top of the Flound Science Building, the observatory area up there. You do not want to miss it. We have a great time observing up there. Please, please, please make your way there. Just look up UTSA Observatory online, and you'll find a page with directions and all of that stuff. We might be doing one on March the 14th, but that's still to be determined. That's spring break week, so we may not wind up doing that one. And then any South Yonah River observings that we usually do on once a month are TBD, because, again, of the Messier Marathon thing and all of that. So just keep your ears and eyes open for that stuff. For SAAA, every Wednesday at sunset, observing at Raymond Remkus Park. Don't want to miss that. There's at least 2 observing events up here, but I think there's actually more on their website listed, so do go to their website and look at their calendar. Guadalupe River State Park observing March 8th, and Crescent Bend Nature Park observing March 15th. And then at the Scobie Planetarium, every Friday night, except for next week's Friday night, the spring break Friday night, they're doing planetarium shows there, and the first Friday, SAAA does observing there. So that's a rundown of the events, and we'll go ahead and close out with these beautiful images here, so I'll give it to Jasmine for that.
Thank you. Yeah, so always, in the chaos of things right now, I like to show good images to just make us think about everything out there. So we have a new one from Hubble of the Veil Nebula. You've probably seen there's an old image of the Veil Nebula from Hubble. It looks really, really cool, but this is a new one. Then we have James Webb NGC 2283, and then UGC 5460 from Hubble. So enjoy these images.
And that is Astronomy News. Thank you very much.
Great job, as always, Caleb, and thank you, Jasmine, for rolling on. That was amazing as well. As you see, I'm wearing my Europa Clipper shirt today. I'm very excited about that Mars flyby. The next stop is Earth, actually. Yes. So we'll see that again. Yeah, December 26, not 25. December, yeah. But of 2026, right? Yeah. Just some fun facts from that. So SIMP is a French survey, for your information. It's a French survey. The Punch mission, it's been really amazing to see its outreach. For such a small mission, it's had one of the best outreach, I think, of anything. I'm sure many of you will remember the punch cards we had prior to the solar eclipse. That was, and we still have them. If y'all use them, then great job. Thank you for supporting the Punch mission. And then the lunar eclipse, since it's Pi Day, the fun thing is at UTSA, if anybody wants to, but we're going to be selling moon pies. So I recommend you all get some moon pies for the lunar eclipse on Pi Day. It's got to happen. All right. Our second speaker, we should all know him very well at this point. It is our very own Aaron Deleon. He was born and raised in San Antonio, and he recently became a PhD candidate right here at UTSA in the Joint Space Physics program. Woo! With SWIRI. He studies and characterizes near-Earth asteroids using radar observations from the Arecibo Observatory, RIP. Aaron enjoys long walks on the trail, I can confirm that one, and a rotating multitude of hyper-focus hobbies. Ask him later what his latest hobby is. Spoiler, it's DVDs, because streaming sucks. Yes, and of course, Deleon, the lion. There's Aaron the lion. And without further ado, here's his presentation with, and this is a doozy, folks, his drinking word.
Asteroids. Thank you. I'd like to thank the Academy. Yeah, so I'll be talking about our first and last lines of planetary defense. Cool, the satellites are moving. That's a Microsoft design. To start the talk, I would like to start on a down-to-earth, pun intended, somber little part. We are in an era where we as humans have the technology, the capability, and the know-how to directly save ourselves from existential dread. Like, we are in that era where we can send something into space and say, you're not going to hit us. We're going to save ourselves. That is something that is quite literally unprecedented, something that has never been done before on Earth. So that's just a very cool thing to realize and carry with you as you live in this world. Now to more mundane matters, some definitions. So first, I just want to make sure everyone's on the same page. What is a near-Earth object, or an NEO? It's just an object whose closest approach to the sun is about 1.3 AU or less. Object is very general. That includes comets and asteroids. And then a potentially hazardous asteroid is an asteroid that has an orbit that I wasn't expecting that one. That comes within 0.05 AU of Earth's orbit. That's about 20 lunar distances. That's very, very close. And is roughly 450 feet in diameter or bigger. Poses a major threat, so it's potentially hazardous. And then, just to teach you a little something. So I think we've all seen 2024 YR4 in the news lately. Show of hands, we've all seen something that's going to hit us, it's not going to hit us, it's going to hit us, it's not going to hit us. So what does 2024 YR4 even mean? So when we name asteroids, we didn't expect that one. We have the year of discovery and then some letters that indicate when it was discovered. So we split the months in half. So January 1st through the 15th would get A, the 16th through the 31st would get B, and then every asteroid discovered, I expect full participation. So every asteroid discovered in that half of the month would get A, B, C, and so on. So YR4, we don't use J. It's confused with I. It's a whole thing. So YR4, that would be discovered in 2024. The fourth YR, or the 118th object found between December 16th and December 31st. So it'd be YA, YB, YA1, YB1, 2, 3. Do that. It's 118. I did this like 5 times. I had to correct myself 5 times. Anyways, we're on the same page. Now, what is our first line of planetary defense? It is knowledge. And I think we can all agree the best defense is knowing the offense's plays. For those not in the know, every single one of these coaches was on a team that was convicted of stealing the other team's plays. So Bill Belichick in 2008, AJ Hinch in, well, it happened in 2017, but then the Astros, whatever. And then my favorite, Connor Stallions, that guy right there with Jim Harbaugh. Jim Harbaugh dipped out. Anyways, okay. So our first line of defense is knowledge. What knowledge do we require? We need to know that the object exists. We need to know that it is there. But then we need to know where it is. Where is it going to go? Then we need to know about its physical properties. If we are to intervene, if we are to defend ourselves, we need to know what it's made out of, all these other things. And then we also need to know how much of a threat level does it pose to us. And so this image is 2024 YR4 moving across the sky. And I like to sum this up in 3 simple questions. Will it hit us? Will it hit us hard? And will it hit us twice at the same time? In other words, is it a binary object? That's happened. It's a thing. So first, how do we find the objects? The most ubiquitous, predominant method of finding objects is sky surveys and dedicated observatories. There's no other better way. So pictured is the near-Earth asteroid tracking. Thank you. The near-Earth object tracking telescopes in Hawaii and California that were operated by JPL. Then we have the Lincoln Near-Earth Asteroid Research Survey. Full participation. Thank you. This one has a very interesting military history. I implore you to look it up. We have the Lowell Observatory Near-Earth Object Survey, or LONIOS. Then the Catalina Sky Survey, and Spacewatch. Spacewatch is actually really cool. That's their whole gig. It's not the big one. That big one, not the big one. It's the two little ones on the sides. But Spacewatch is really cool. That's their whole gig. They watch near-Earth objects and track them and find them. So for each of these sky surveys and dedicated observatories, I have listed how many objects were discovered by each of those. In total, since earliest of 1993, over 500,000 objects have been found. That is insane. That is, like I said, we have the capability. We are finding these things. It is so cool. And then this isn't a perfect method. We can't always find them. Sometimes a couple of them go under the radar. So every now and then we have to use, wait for it, the oh shit method. They just happen. They just fall. We don't know that they're going to come, and then they happen. One of the most recent ones was Florida in 2019. It was recovered by a lot of Ring cameras for some reason. Before that was wide news coverage was in Chelyabinsk, Russia in 2013. Covered by a lot of dash cams. They have a lot of dash cams in Russia, which is very interesting. And then also the Peekskill meteor in 1992. A couple of fun facts about that one. The only reason it was recorded by so many people was because it was on a Friday night and everyone was watching high school football. And that asteroid hit a car. It hit a red Chevy Malibu. Apparently that car was bought for $300 and was sold for $25,000. You want to make some money? Get hit by a meteor, I guess. I don't know. And then, okay, so we find the objects. Now we want to know where they are. That one's more or less, I will say, straightforward. It's not straightforward at all. We need to use what's called orbit determination. Essentially, you look at it a bunch of times in optical or with radar, optical meaning like in the wavelengths that we can see. You look at it over many, many days. You track where it's at, how fast it's going. Different methods are involved for optical or for radar, but eventually you determine the six variables that determine its orbit. Some of those variables have other variables involved, so like you need many, many days, you need many, many data points, but that's why we have Spacewatch. That's why we watch asteroids. That's why we do this thing, because we want to know where they are if they're going to hit us. So now we know they exist. We know where they are. So the next question is, how do we characterize them? I got to participate in my own drinking game. So we characterize them. This is what I do. This is my research. We just look at them. We observe them in different ways. One of the first ways is in the optical, so the wavelengths that we can see. This picture is, it's a rotation phase, which is to say we looked at it enough times to watch it turn, essentially. But with the optical, we can know about its rotation period. We can determine if it's a binary or a tertiary, if there's three of them. We can determine, with enough observations, as I just mentioned, the orbital trajectory of it. We can well, that's about all we can determine with optical. The advantages of optical are they are the most abundant telescopes. You don't need a big telescope to look at an asteroid. Full participation, I hear, woo! And then also, another benefit for optical, you can do stellar occultation. So you can watch it pass in front of a star. You do that at like different, not quite latitudes, but like you space yourself out enough and you can find out how big it is and what the shape of it is. The biggest caveat though, limited resulting information. You don't really get too much about the object in question. So the next thing we can do is infrared. With infrared, we can really nail down the size of the asteroid. Got you by surprise on that one. And then we can also learn about the composition. We can get hints at kind of what it's made out of. Not quite like to a 100% degree of certainty that like, oh, that's made of all rock or all metal, but we can kind of know what it's made out of. The biggest caveat with infrared, it must be observable by a space-based observatory. We can do infrared from the ground, but it's very hard. It's best from space. And right now, JWST is, correct me if I'm wrong, I believe it's the only infrared telescope in space that is operating at this moment. I think NEOWISE was mission end. Spitzer is definitely mission end. I think it's just JWST. And then after that, SphereX. Oh, you're saying Hubble? Yeah, Hubble can peek into the infrared. We're getting technical now. So yeah, there's a caveat with infrared, but we can really nail down the size. One of the best methods, this is what I do, radar. So with radar alone, you can learn the size, you can learn the shape or more the volume, and then with those two, you can learn the density, which tells you so much about what it's made out of, how many air pockets or vacuum pockets, I guess, are in the asteroid. You can learn the rotation period, the orientation, which is very important. The orientation, if it's pointing to the north or to the south, tells you in which direction it's rotating. So we're rotating prograde, which is just to say a direction. Retrograde would be the opposite direction. Why do you want to know that? If you want to hit it, you need to know which direction it's spinning. And then you can also learn over a couple of observations its orbital trajectory to a very, very accurate degree. And then also, almost immediately, binarity. Is there two objects that look like this one object? The biggest caveat with radar, though, it needs to be close. It cannot be far away. It needs to come within, I really don't know how close, but close. It needs to be very, very close to observe in high fidelity to be observed with radar. Okay, so now we know they exist. We know where they are. We've characterized them. What do we consider a threat? That. It's going to hit us. That's a threat. A better question, how do we quantify the threat? One of the first ways of doing this was developed was called the Palermo scale. It's a logarithmic function that takes into account the impact probability, the time until impact, and the annual probability of impact with energy E in megatons of TNT. It took me so long to wrap my head around this function. Like, it works, not great. In essence, is the threat above the background level of day-to-day normal impacts? How much does that tell you? I don't really know. The higher the number, the bigger the threat. So we developed another way of doing this called the Torino scale. Bright flash all of a sudden with a white background. The graph was white and I couldn't, it was a whole thing. So the vertical axis is kinetic energy in megatons. The horizontal axis is probability of impact. The closer you get to the right, the more probable impact, probable the impact is. And just to wrap our heads around how much energy we're talking about here, 1 megaton is 67 times more powerful than the bomb dropped on Hiroshima. So we're talking lots of energy here. What I think is funny about this scale, when like you're looking at it in this graph, below 1 megaton, it's like, oh, not threatening. That's a 0. Even if it's 100% probability of impact, it's a 0, not threatening. But that makes sense because if it's below 20 meters, it's probably going to burn up in the atmosphere and it won't hit the ground and cause devastation. But this graph is not the best way to convey to the public you're at risk, so they wrote it all down. They gave some very descriptive paragraphs to say for each threat level and also some nice color coding. Green is good, red is bad. And only 3 asteroids have been above a 1 ever in history since we've had this scale. The first one was in 2004. It was Apophis for 4 days. And then 2004 VD17, I taught you what it means. You can you can backtrack when it was discovered. For 3 months, it was a 2, and then 2024 YR4 most recently for 24 days in 2025. I don't think that was all in 2025, but that's neither here nor there. So yeah, we haven't gone above a 4, which is good, because we know nothing's going to hit us really hard. No asteroids. There was a low. That one's fine. There was a low. Okay, now, so that's all the knowledge we can possibly obtain, that they exist, where they are, what they look like, their physical properties, and then how much of a threat level they pose to us. So our last line of defense is intervention. And I think we can all agree the best intervention method, you call Bruce Willis and the boys and you send them out. That's by far the best method. And dread. So some intervention methods that some scientists have come up with. The first one is a nearby nuclear explosion. So just bam. I spent an hour making this animation, so we're gonna watch it again. Yeah, just like that. It happens just like that. Animations in PowerPoint is crazy. I highly recommend learning it, but I also don't. It's a pain. Anyways, so a nearby nuclear explosion. You strap a nuclear device to a rocket and you send it to the space rock. That's insane. The biggest risk is fragmentation. You send it out, if it explodes too close, you get more pieces. That's not good. If you think about it, it's like, well, if the pieces are small enough, they could burn up in the atmosphere, but I don't want to take that risk. That's not something I want to think about. So, and then also with this method, it's best for large objects. It's not really considerable for anything smaller than, I don't know, say 50 meters or like 150 feet. This requires some warning. I say some, I have other levels of warning, but I say some because I don't think theoretically it'd be that hard to strap a nuclear device to a rocket and send it out like really quickly, but you need to know it's gonna happen. And then the biggest caveat, it's untested. Never done this before. Who knows? It should work. Will it? I don't know. And then the next method is called a gravity tractor. I should have put this in quotes because it's not that sci-fi. So another animation, you just send a bunch of mass at it over a long period of time, and eventually you do it enough, it moves. But it takes a long, long, long time. I'm not going to make you sit through that one again. It takes a long time, so one of the risks is you don't send enough mass to alter the course. You could send one lump sum. You could send a bunch of sums, a bunch of masses to it. We could calculate it, but again, it's like, do we get close enough? Will it happen? This is best with small targets. Above a certain threshold, it's almost like you're doing nothing. And then this requires very advanced warning. This will happen so slow, it will take years, if not decades. So we need to know what's going to happen. And if it's a small object, why this method? There are better methods. And again, untested. One of the best methods, the kinetic impactor, similar to the nuclear device, but instead, there it goes. You just hit it. You don't send a bomb, you just hit the thing. Best with small to medium objects, requires advanced warning, simply because we need to know what's going to happen and we need to characterize it. We need to know where it's going. We need to calculate its orbital trajectory with enough certainty to hit it, which is pretty hard in space. One of the other caveats is assured impact energy. You need to impart a certain momentum to alter its course enough to not hit us. We can calculate it, but again, lots of uncertainties wrapped up into that. And then also the biggest risk is missing. That would suck. And we've done this already. The double asteroid redirection test. We hit it. We really hit it. It was really cool. And we hit it so hard, we changed its orbit. So we hit a moon of an asteroid, which is like a very good. That was a low. I didn't say it enough. Thank you. So we hit a moon. We hit a small asteroid that goes around a bigger asteroid. And we changed its orbit by 32 minutes. I think the like a mission success was something like 7 minutes. We did like 5 times more than that, which is crazy. Like I said, assured energy. That was definitely assured, but we learned a lot about when stuff falls off, stuff happens. How it happens, we don't really know. And here's the wackiest intervention ideas I came across the internet. First one, ion beam shepherd. You send a rocket to an asteroid, and you park it at a point where its rocket engine hits the asteroid, and that imparts a force that pushes it. However, that rocket also has to have another rocket engine that keeps it stable. So you have this like double thing going on. It's super weird. You also have a focused solar energy beam. I don't know how you send a big ass lens out into space to focus enough energy to ablate an asteroid. That's a lot of energy. Go ahead, I guess. Then good old-fashioned laser ablation. You just strap a laser to a spacecraft and you hit it with your laser and it ablates. The ablation acts like kind of like a rocket engine. The stuff that flies off imparts a force that pushes the asteroid, and the idea is to push it enough to change its trajectory that it misses us. It wouldn't be like we're like kicking it out of the solar system. And then you have a solar sail. This one takes a long time, and solar sails are not like the most tested technology. We know they work, but how you would strap it to an asteroid, I don't really know. And then my personal favorite, painting. You paint the asteroid with a material that either absorbs or reflects heat, and that heat affects the imparting radiation pressure from the sun. And like this is a known thing. It's called YORP. It's its own field in itself. But that radiation pressure makes the asteroid move. But this would take like decades. So I don't think we know of any asteroid that's going to hit us like so big. It would have to be big. If it's going to hit us in decades, it has to be really, really big. But I don't think we know of one that's like that. So it'd be kind of pointless. We can just hit it with the kinetic impactor. Anyways, what are some future planetary defense endeavors? The main one is Apophis. In 2029, it's going to make a close approach. It's going to come less than 1/10 of the distance to the moon. That is stupid close. The moon is close. 1/10 of that, that's stupid close. And so OSIRIS-REx went to Bennu. I've confused it with Bennu and Ryugu. But it went to Bennu, did its thing, and then now that has been kind of extended into a second mission called OSIRIS-APEX. And that same spacecraft is going to go make a flyby of Apophis when it gets very, very close to Earth, because we think when asteroids get very, I didn't expect that one, when they get very, very close to a big mass like Earth, they should change. There's going to be like some tidal forces, kind of like some asteroid quakes going on that change the surface a bit. And so it'd be cool to observe that. And there's also a smorgasbord of other people planning to want to go to Apophis. So much so, we may have a space traffic problem. New things in human space development. That's kind of like the only thing. Apparently, China's going to try to hit, I think it's 2004 VD17, I think. Apparently, they're going to try to hit another asteroid like we did. It's another space race, I guess. But is China going to do it? Probably. I don't live in China, so. If you're ever curious, JPL has a website called Sentry, or the URL is up there. But you just search JPL Sentry. You can look up, is something going to hit us? At what probability will it hit us? How big is it? When will it hit us? You can use the Palermo scale, which you kind of learned about. Higher the number, the more threat level. And the magnitude, which is an analog for size. But I picked things that are going to happen, impact probability of 2.001, I believe. Yeah, 0.001, which is like a 1% chance. 1% chance, a Palermo scale of -8, which is very low, but apparently high. Like I said, it's a very difficult logarithmic equation to understand. And it's kind of like, no, nothing's really going to hit us soon. And if it's going to like pass us, the potential impacts I think is crazy. Over 100 for these three. That just means like it's going to get close. It could hit us. It probably won't. But it's a fun thing to go and explore. So that's about it. To summarize, our first and last lines of planetary defense. Our first line of defense, knowledge. The best defense is knowing the offense's plays. And our last line of defense, send out Bruce and the boys. And that's about all I got. Thank you, everybody.
Great talk, Aaron. Thank you
Thanks.
for that.
Thank
The Italians really cornered the market on the scales, didn't they?
They did. They did. They really. Oh, it took me so long to figure out why they're named. They named them after the locations the scientists were at, where they convened to come up with this. That's not the most obvious. I think that's the most diplomatic, but it took me a long time to figure that out.
There you go.
Yeah.
All right, we'll get started. Our first question is, are there no observatories in the southern hemisphere that are looking for these objects?
Great question. There are all those sky surveys and observatories I mentioned. I didn't say this in the talk. Those are all that's just United States. That's not considering Europe, not considering China or Russia. There's one that I know of in the southern hemisphere. This is why I said to look up the history of the Lincoln Sky Survey. It's called Linear. So that sky survey technically ended in 2013. However, it was transitioned to the Space Surveillance Telescope. That telescope stopped. They took it apart in 2017 and they shipped it to Australia, where it's now a co-effort with the Royal Australian Air Force and the U.S. And so that's our monitor in the southern hemisphere. I'm sure there are other sky surveys and observatories that are also looking at these things, looking at asteroids.
Woo.
But talk's over. My bad. I'm doing too much. But yeah, I'm sure there are some in the southern hemisphere. There are definitely way more than the ones I mentioned. It's not just like there was a plethora of just U.S. alone sky surveys. That was maybe like a quarter of them.
Is there a reason that we did not know that the ones that came to Earth recently came? Were they just too small, moving really fast, or in an undetectable spot?
All three. If they're too small, they're really hard to see. They have to be a certain brightness for them to be, I'll say, noticeable. Kind of too fast in the sense like it was there one day and then it's over there, but we looked over here the next day. So it just moved out of our frame, and the third one was, what was the third one?
Undetectable spot.
Undetectable spot, yes and no. Like the poles would be hard to see. There's a couple of spots where like maybe all the telescopes are not looking at once. So it's a matter of all three. And then also like the one in the 90s, we just started planetary defense endeavors. So that one was going to be hard to see. Chelyabinsk in Florida, probably just too small to be noticed immediately. They could have been in the data, but it's hard to say. It's all of those factors mixed into one.
Very interesting. All right, remind everyone to send your questions into the number. I wrote down a few. Are we going to be able to see Apophis when it comes by?
Yes.
Yeah. Okay.
Yes, it will be visible with the human eye. It would be below 6 magnitudes when at its closest approach, which is freaking crazy. That's how close it is. Yes, you will be able to see it. I don't know how fast it will be moving.
Okay.
Pretty fast, but yeah, you'll be able to see it with your naked eye in a dark sky. It's like going to be like just below 6 magnitudes, which is the naked eye threshold. So go to a dark sky, go to South Llano, go to Big Bend, go anywhere northwest if you're in San Antonio.
Very cool. Okay, I'm biased, but talk more about those stellar occultations.
Oh, stellar occultations. Yeah, I can talk more about those. So it's actually like very, very simple. You set up a lot of telescopes, spaced. I really don't know what the distance would be, but you space them at ever so distance, and you watch that star. What'd you say? 200 yards? Yeah, there you go. That's actually less than I thought it would be. Yeah, that's pretty good. So yeah, you set up a bunch of telescopes 200 yards apart, and you look at this star and you watch the telescope pass it. The thing is, every telescope that is separated by that distance will see ever so slightly a shift in the angle at which the asteroid passes the star. And so if you have enough, they're called chords, you can line up those chords and you can see when the asteroid first covered the star, when it uncovered the star, and you do that for each chord, for each telescope, and you draw this diagram that kind of plots out the shape. And it's a very simple, very robust method. And you need to know what's going to happen, though. That's the thing. You can't do it like, you can't just go watch a star and be like, I'm going to wait here for something to pass. That's not going to happen. You need to know in advance that something is going to pass a star that is not only bright enough, but also like detectable enough, or not detectable, findable enough, or markable enough to point to it. Yeah.
Very good, thank you.
Oh, I know why you said that, because you have a whole thing. You have a whole UV thing with stellar occultations.
Oh, yeah.
This guy set up a whole entire method of how to do this.
Well, not those, but it's all interesting. Stellar occultations are all cool. I like this question. Are those Starlink satellites, are they interfering with asteroid observations?
Yes. To the sense of they're interfering with all observations. It's a problem in astronomy. They're becoming so ubiquitous in the sky that astronomers are starting to develop dedicated methods to remove Starlink satellite detections. It's an entire thing. Astronomers complained to Elon Musk, and he said, I'll make them darker. He kind of did, I guess. They got a little darker, but they're still very bright. And yeah, you have these trains. Has anybody seen a Starlink train? It is so creepy. Like, seeing that in the sky is so creepy. Yeah, it's just dot, 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 dot. Like, imagine, so weird. But, so like, they're a problem across astronomy in general. So, yes, with asteroid observations. But I don't know to what degree specifically with asteroid observations. But that's a very good question.
Yeah. Remember the one at Big Bend?
Big Bend, yeah. That was weird.
Are dual body objects that common that they're significantly more concerning? Or I guess
binaries?
The binaries, yeah.
Yeah, they're 15%. Binary, near-Earth objects, 15% of near-Earth objects are binary asteroids. And we have evidence on the moon of a binary asteroid, or probably plural, of binary asteroids hitting the moon. So you have two things at once hitting the same object. And that's crazy. That sucks. Once is enough. Twice? I mean, come on. Like, that's just like a giant middle finger. But yeah, they are definitely enough of a problem to worry about them. The nice thing about binaries, though, most of them are not what are called equal mass binaries, which is you have a binary made of two objects that are about the same mass, obviously equal mass, but so they're about the same size. Most binaries are not like that. So the satellite, the secondary, is smaller, and so there would be a chance it would burn up in the sky. I'm not going to take that chance. I would want to know, how big is it? What's the size ratio? Is it going to burn up? Should we hit both? Should we hit only one? Who knows? But yes, they are enough of a problem to worry about.
Very interesting. All right, we'll finish off with a fun one. What's your next hobby going to be?
Hobby? Ooh. So my current hobby is like DVDs and like acquiring DVDs, because down with streaming. So my next hobby is going to be burning those DVDs. It's an entire other subfield of DVDs. Like, it's not piracy. It's not illegal. It's illegal when you share them. So you're good.
Yes.
Yeah.
Yeah, for the kids these days, it means copying. Okay. Yeah. Let's thank Aaron once again. What a fantastic talk. Stay up here, though, because We're
This is my job. I got to stay up here. So
all right. For those of you that have to go, we thank you for joining us tonight. Our next event will be Wednesday, April 5th. No, that's today. So no. Second, Wednesday, April 2nd, the day after April Fools. So we're not fooling you. We have one or both speakers lined up already? Both, yeah, so we already have speakers lined up. So hopefully I'll get a flyer out early to y'all. I am at a conference next week, so no expectations. But we're excited about that one. Once again, if you have to leave, we thank you for coming. Make sure that you check out and that you tip your staff well. They do a great job, and we thank them. But for those of you that are going to stay, guess what? It's trivia time. So sit back, relax. We'll come back by with your sheets. And remember, 4 to a team, and assemble. No cell phones. The max group size is 4. Write only the letter for the multiple choice answers, A, B, C, D, E. And no cell phones allowed. We want this to be as fair as possible. What? Yeah. Yeah. What's her name?
Oh, what's our name?
All right, question 1.
The stars at night in this Jane Austen classic, Edmund Bertram, Bertram and Fanny Price enjoy a night of stargazing, pointing out Arcturus, a bear, and Cassiopeia. What's the question? Oh, okay. Name that book. In this Jane Austen classic, yeah. They're pointing out constellations. Is it A, Mansfield Park, B, Emma, C, Jane Eyre, or D, Persuasion? I have no idea. The only one I know is Jane Austen.
Did Jane
Or Jane Eyre.
Austen write Jane Eyre?
Yes.
She wrote a book with Jane?
It's
That's
a
very
very
self-centered.
It's a very common first name.
No, I don't think. I think that'd be like me writing a Michael book, you know.
It could be like a. Is there like a category of like. Not quite a memoir, not quite a biography, but like you're writing about your life, but.
A fictionalization?
Yeah,
Oh,
like
yeah.
like a fictional
Yeah.
biography kind of.
Yeah.
Or a biographical fiction.
Yeah, I've seen that. Well, you know.
I read a fictional story that was written as a biography, and it was really cool.
Yeah, there's an existential like horror novel that one of my friends is reading, and it's written as like somebody going through someone's notebook or diary or something, and it gets like weirder and weirder, and you just start to have issues telling what was
Yeah.
real and what was not. It's
I
really
wouldn't know the name of that book.
I'll have to ask him.
Yeah.
I'm not gonna ask him tonight.
Sure.
Yeah, definitely. So, I figure.
It's either C or A, in my opinion. I don't know enough about it. I don't know enough about it.
I don't read. I've never read any of these books.
I'm trying to read more classics this year.
Yeah?
My goal this year is quality over quantity.
Okay. So you're the anti-quantity.
Yeah.
Quantity over quality. All right, I think we'll come back if you need more time. So we'll move on to question 2, which is inside the Louvre Museum in Paris, one finds this sculpture depicting which Roman god fastening his sandals. Is it A, Mercury, B, Jupiter, C, Neptune, or D, Apollo? Hint, this Roman's Greek counterpart is Hermes.
I think we should have had a hint on the first one.
Apollo's the sun god.
Yeah.
Is he also the messenger?
Hermes is the messenger.
Yes, I know, but is Apollo?
No, Apollo's the sun god.
I think it's Mercury.
If Hermes was the messenger,
Hermes is the messenger.
then it's Mercury.
Why I thought it was like Mercury.
That's why the messenger mission went to Mercury.
That's it. You're part of the Starfuckers now.
No, and that's with the sandals. That's the sandals because the sandals had. Didn't the sandals have wings on them?
Yes.
Is that
and you
Hermes?
can tell the hat.
Oh,
The
yeah.
hat has the wings.
I thought Pan had the hat.
Several things.
It's like the whole thing.
They all went to the same haberdasher.
That's why it's the pan.
Yeah. What'd you say?
They all went to the same haberdasher. All right, we'll move on to 3.
Question 3. Ganon did nothing wrong. In the best-selling video game Legend of Zelda Tears of the Kingdom, what periodic astronomical event causes all villains to respawn? Is it A, a passing comet, B, a solar eclipse, C, a sunset, or D, a blood moon? Michael was assured as ever of that answer.